microphone?
Yeah.
Okay.
Told me it sounds down.
P is greater than 2.
Perfect.
Great. Is larger than
Okay, everyone, let's go ahead and get started. So next up, we'll have a talk from Keith Rush, who's a staff research scientist at Google DeepMind. And I think Peter's tutorial actually set us up nicely to have this transition in that Peter mentioned that maybe you can think about federated optimization as distributed optimization in the wild. In that sense, I think a lot of the early work in federated optimization, we had to do a lot of talking about how this differs from distributed computing, distributed optimization, traditional data center optimization. And maybe what you can see is that, as those federated optimization methods have advanced, some of those techniques looking at distributed optimization in the wild now in turn are useful also for data center distributed optimization, especially thinking about things like pre-training of LLMs. So we might hear a little bit more about that in this work.
Yeah, I guess probably you will. Actually, hi Peter. I've probably never met in person, but if I have met Peter once or twice, he's probably talked a lot about a lot of algorithms. I'm going to talk almost nothing about no algorithms at all. I'm just going to talk about applications, really. I realize you gave me a whole hour, so hopefully I won't use it. 40 minutes maybe, So don't worry. Hopefully your attention won't be too strained. And I'll probably make a bunch of dumb jokes because I always do. Oh, you know what? This used to work. Up, down. OK, maybe I'll just do here. OK, yeah. Who am I? That's me. I guess you can tell. I am a mathematician by training. I was a pure mathematician. It was really fun. I love being a pure mathematician. But you know what? I was in grad school when the deep learning revolution was happening. I was dated to AlexNet in 2012. I was in grad school 2013 to 16. And it was pretty clear to me that this was really going to matter. We were going to be able to do a lot of stuff with ML. And it would really change the way that math worked. And so I was like, you know what? I got to get into this ML thing. Google seemed like a good place to go. So I came in as a SWE. Eventually, I jumped to the research scientist track, moved to GDM, moved down here. Previously was in Seattle. This worked again. You may remember me from some work in federated learning, or for some more recent work in private learning. Adam's here, too. He's on one of these at least. Also, never met him in person until today, so that's nice. Or some even more recent work in scaling very, very big training, which is, normal thing we like to do today. Because I'm a mathematician, I never really changed that culturally speaking. All opinions and thoughts are my own. Everything's mine. Okay, someone's sending me a Cielo review right now. And silence that. Often in my day-to-day world, I think about what next-gen learning systems are going to need, particularly from the perspective of both algorithms and systems. Often I think we shouldn't be trying to invent something new. We should be trying to apply things that already exist. It's like, maybe in industry we should usually be trying to do that. And I think you'll see that in the rest of this talk here. OK, so now we're going to start the first half where we talk about what they're going to need. OK, well, to talk about what they're going to need, it's useful to talk about what they are now. This is probably not going to be a surprise to many of you, but they're big. OK, I had all these images be AI generated. That's one of my great applications. I hate making pictures. I hate making plots. I never remembered the API of matplotlib. And now I never have to. So it's really nice. OK, how big? I'm going to throw some numbers up. So this is all scientific notation, right? So E26 is 10 to the 26, right? Grok 3, which I don't even remember which one they're on right now. Is it 4? Whatever. Hard to keep track. Is supposed to have been trained with, let's say, 5 times 10 to the 26 flops. The traditional supercomputing methods can't really match this. El Capitan is I think it's the biggest one. Yeah, leads the top 500. It's at Lawrence Livermore National Labs, so it's just down I guess we're not on the peninsula. I don't know what you call it. Down the East Bay, I guess, on the other side, right? You got to get to the other side of the hills. Has a throughput of, let's call it 1.7 times 10 to the 18th flops per second. So if you do this math, this would have taken about 5.6 years to do this training. 5.6 years is a long time in the world that we're currently in. It's about the time from GPT-2 to right now. So a lot has happened between those two. I think, is GPT-2 the one with the unicorn sentence? Does anyone remember that? Is that right? Is that GPT-2? It was like really, no, is that 3? That was 3. Okay, so this is even before the unicorn sentence. The like striking, oh my God, it did one really coherent made up example. So that's how long this time was. Interestingly, when I was writing this, I had Gemini estimate for me what is the absolute peak throughput of all mobile phones in the world, just if you forget about everything and you just focus on flops per second. It's about 5 times 10 to the 21 flops per second. Okay, is that a hallucination or real? I really have no idea, I didn't check it. But if you take that number as real, you could have probably trained Grok 3 in about 17 hours if you could address it all. But it also reminds me of that, I think it's the scene in the HBO show Silicon Valley where they like blow up everyone's phone or something, right? Yeah, so there's a lot of compute out there, but not a lot in the old traditional supercomputing model, relatively much less than we are using. Okay, so it's big, right? Usually you think of the world's biggest supercomputer as big, and I just told you that it's actually quite small compared to the amount of compute we're putting in these things right now. Does that indicate we maybe should be doing something completely different? Maybe, but I'm not going to talk about that. Okay, so it's big, and how quickly is it growing? This is all public data, obviously, because I can't come up here and talk about private data. Grok 2 to Grok 3 was 10x in 6 months. Anthropic's compute's probably growing about 5x a year. That's another public estimate. I plotted that against, here you go. This is a matplotlib plot that I didn't do because I would never do this. Way too much work. Plotted this against the way Moore's law works, right? 10 years of Moore's law compared to 10 years of 5x year-over-year growth. That's whatever, what is that? About 10 million x up at the top and 32x down at the bottom. So that's a pretty big gap, right? This is a log plot on the left. That's a very large gap. So how are you possibly going to do it? Well, there's only 2 things you can possibly do that I'm aware of. I mean, besides dramatically change the computation you're running, which are specialize and distribute. Okay. Pause. Won't it all stop? Maybe. I don't know. Some people think so. The Earth probably can support it. Power is important. But there's also a lot of power that hits the Earth. Maybe we'll finally build a bunch of nuclear power plants or solar data centers out there in various deserts. Will the data be there for it? Another big question. RL, learning from experience, a bunch of untapped data sources, and giant incentives to do things like synthetic data, whether this works or not. It's hard to do synthetic data, but people will try. Indicate that I think I'm personally willing to bet that the data will be there. I think it's also important to ask, is there any reason to keep doing it? Are we just slopifying the world? I don't know. That's probably above my pay grade, I think. Okay. Oh, where's specialization? Okay, next. I forgot my ordering my own slides. How can we possibly make this all work? I'm going to talk about, I guess, a perspective on like normal data center training that makes, a lot of the people in this audience it'll make a lot of sense to you. But it's a bit weird to a lot of normal data center people. And I usually call it distributed first. It's very much anchored in the kind of federated world. I'll try to talk about one view of one way you can read the history. It's a Google-centered way because when you're at Google, you have to live in the Google universe. You don't really have a choice because your brain does it for you. Okay, so we'll go back a bit to specialization because I think it's worth touching on because it still is going to leave a gap. GPU and TPU are like the main specialized computers for doing this. People are doing more complicated things, right? People are doing the Cerebrus wafer thing. People are graph cores doing something. People are burning architectures into chips. People are probably burning weights into chips for pretty good bet that somebody's doing that. But GPU and TPU are the main ones, right? Okay. How quickly is their throughput growing? Again, this is a public estimate that for fixed precision, they're growing at about 1.5x a year, which is more than Moore's law, right? Moore is doubles every 2 years, I think, or that was the peak. Is that right? Doubles every 18 months? But it's not that anymore. So this is 2.25x in 2 years, right? You can get a perf boost by reducing your precision. Going FP32 to int8 gave a 10x perf boost. A lot of people do very reduced precision training now, like int8. So let's just throw on another 10x there by it's not quantification. What is it? What's the word I'm looking for? What does quant mean again? Quantization, that's the word I'm looking for, right? Okay, let's assume we can do more quantization and 10x it again. So compared to 5x every year, this buys us about 3 years or a bit less. And that's really hard. Let me tell you something, quantizing training really, really low when you have a really big model is not easy. It is difficult. Difficult to do, unclear how far it can go. So I'm going to tell you 10x right there is quite a generous number. Okay, so if we're going to buy that this thing is going to keep scaling, and again, Grok 3 is pretty old by now, right? I think they're on 4. They got to be on 4. Has to be. If this thing's going to keep going, distribution is going to have to be a key part of it. And if we're going to, just look at these numbers here, 1.5x a year is the throughput. These are all one-time boosts, right? How you can't get lower than whatever 1-bit training. It can't be done, without just completely reinventing what we do. So maybe that's what's going to happen. But the quantization stuff is one time. Just plot all the lines. You're going to have to distribute more as time goes on. Okay, so I hope this crowd probably doesn't need a lot of convincing of that, but I think it's true. All right, what does distribution look like today? Typically, it follows a pretty familiar paradigm. Take a single program that we know pretty well, which is computer derivative, and make it bigger. Scale it up. All the various P's that we all know and love, what are these? Tensor parallelism, sequence parallelism, expert parallelism, pipeline parallelism, fully sharded data parallelism, and data parallelism. Those are all the P's on here. There's probably more by now. That's what these all are, right? Tensor parallelism basically means you split your matmuls up, your matrix multiplications are in multiple places. Sequence parallelism is like you're doing this giant sequence processing, so you split the sequence in different places, you route the tokens around where they need to go. Expert parallelism is you put the different experts on different devices if you're training a mixture of expert model. Pipeline parallelism, right, is you split the layers up and now you do small batches and fill up the queue going forward and let the derivatives come back going backward. So that's where you get all your crazy DeepSeek pictures from. Fully sharded data parallelism is, yes, you split the weights, but then you gather them right before you do your matmul, and you also split the batch along the same dimension. Data parallelism is model replication. That's the one that's normally called pure data parallelism, or true data parallelism. Okay, but all these are about partitioning the compute from our one single program that we're asking everybody to compute and making it bigger. Okay, but there's a different paradigm we can be following, which is to surface some characteristics of the distributed system that we're programming and ask the algorithm developer to deal with those directly. That's kind of my view on federated learning, basically, is that it's kind of like that. Maybe it's a bit more like data locality is kind of the fundamental thing, and that's not quite the systems thing, but sure, abstract it. Pretend it's like it's a systems thing because you can't move the data or whatever. I guess I'm probably anticipating my next few slides when I'm saying that, but okay. We'll see. I'll skip them if I did. When we scale, yeah, it's hard, but certain things become free. We should be asking about these things first. I think that the mainline ML research community, the one that is instantiated in all those billion-dollar startups around here, has mostly ignored this kind of concern and focused on the previous one. My claim is that designing and applying algorithms and methods which are intended first and foremost for this kind of setting, I think it's the most interesting problem in optimization ML algorithms for the foreseeable future, and there's a lot to be done here. I'll try to kind of connect this a bit more concretely with FL, but I guess because I'm a mathematician, I tend to talk really abstractly, so maybe I will fail to connect it concretely. But maybe it's already obvious to all of you, and I don't need to. Okay. I was promised to talk about federated learning. Why did I get this like harangue about scale and parallelism? Yeah, this is, I guess, why this is the slide I was anticipating. When I say that, I always viewed federated stuff as like algorithms that target a different computational substrate than is normal. So they have different things are expensive and different things are cheap. Me saying distributed first is kind of just taking this perspective, what's expensive and what's cheap in the system that I'm running, and just transforming it into the training of LLMs. This is one read of the history here. It's not the only read. It's one read of one part of the history here. It's not the only read, and it's not the entire history, but OK. I think you can draw a reasonably continuous line back to local SGD, which is very old. So I feel like I always go back and I'm like, there must be some stuff from the 90s that is like it, and then I think I find it, and then I try again, and then I always fail to find it. But I always find at least 2010. I know there's earlier ones, but I always I just wrote this last night, so I didn't work that hard to find it.
Papers are solo though from
90s, OK. Maybe you can send them to me. I can finally have them forever and not be like, I know there's something from the 90s here. Actually, if you go and find the disbelief paper, which became TensorFlow, you will find these kind of methods in there too. And they trained billion parameter models on like 1 million CPUs and stuff, crazy stuff for the time. But yeah, there's kind of that perspective, which was like, that was always like a weird branch of more normal training, right? TensorFlow was never primarily used for the 1 million CPU big distributed training parameter server case. There honestly probably were some applications at Google that were like that, but I don't know them. Accelerators took over pretty early. Federated averaging used really the same algorithm, but it surfaced the decentralization of the data as opposed to the compute. At least this was my view of it, that like the decentralization of the data was paramount, and the decentralization of the compute kind of followed the decentralization of the data. Obviously, there was tons of research and algorithm improvements in this vein. But now I think that you can view a lot of the work that I've been doing and some of my collaborators have been doing the last couple of years as walking backwards up this chart and going back more to the TensorFlow local SGD view, leveraging a lot of the algorithmic improvements that happened here. Is this going to be a laser pointer? No. OK. Maybe it's supposed to be. I don't know. Guess I can't do the laser pointer. But we are moving. I personally, my work is moving back away from the decentralization of the data and moving to the physical location of the compute as the primary thing, because it is pretty expensive to build really big data centers with their own power plants and stuff like that. So you can't move them around. Where they are matters. OK, I think I broke it by trying to use it in the wrong way. Oh, skip it. OK. Like I said, distributed first. So now we're going to walk through an example. It's back on. We're good. Yeah. I think that you can really capture this perspective in saying that we're just trying to judiciously surface to algorithm developers and programmers all relevant systems features. So you can ask, what's a relevant feature? Not obvious how to answer that question. What's relevant might change. That's kind of where there's a little bit of art, I think, here. I tend to anchor in looking for principles. So MapReduce is one. MapReduce is very common, like primitive, reappeared many places, and it's always been quite good. So a couple of years ago, I started working on enabling the absolute simplest version of this kind of programming, MapReduce style programming through the JAX stack. All it is purely synchronous SPMD, but it surfaces all of your available parallelism axes to you. And it just does what you want it to do. I guess from one perspective, like the way this library is most commonly used today is like PMAP as if PMAP did what you wanted all the time. Yes. But what's the programmer going to do with it? OK. Now, here is where we make a connection to the federated learning algorithmic family. You'll notice my name is not on this paper. So OK, this is a different group of people that I work with quite closely now. OK, from the algorithm perspective, this family, I guess it's in the title of my talk, DeLoco, was really an application of adaptive federated optimization to large-scale LLM training. Well, large scale was actually pretty small scale for today, certainly, but I think even for back then it was pretty small scale. There were already some differences, though, like where's the state? The state matters, right? Like if you're doing really, truly mobile-focused federated learning, state, you really should not assume that state exists in your clients. We kind of have dropped the name clients in this stream of work because they're not really clients. It's more, client always was a weird word to me in federated learning because it's like, it's acting like a server, right? I mean, it's doing the compute, right? It's like, okay. But yeah, so now we call it workers, a bit more like normal distributed system stuff. Yeah, but here, sure, you got stateful everything because you got your worker is a giant data center out in the middle of a desert somewhere. So it makes a lot of sense to put the adaptivity in there. So OK, this is going to be the start of the rest of the story. We moved the initial implementation of this algorithm on top of Dr. Jax, and yeah, we started working together. OK, another little note on like what this all looks like from the programmer's perspective. Surfacing relevant systems features. What exactly does that mean? This is a representation of doing normal data parallel training. Normal data parallel training, you, the algorithm developer, you see single model in, single gradient out. And so you see the input to this whatever river, and you see the output to this river, and somebody underneath you replicates your model and injects a reduction to like synchronize everything. All of your data is what's sharded across these like multiple streams. This is what the slicing looks like to you. System does all the replication, and you see this view that doesn't quite match the physical reality underneath. Did I have two of these? OK, to implement that previous version that we were just talking about, you really need an alternate slicing where you exactly surface the data parallel access to the programmer, where the programmer and the system's view actually like match one-to-one, which is like, I think it's kind of one way of viewing what a lot of like FL style work is like. It's like surface to me something that matches what the system has. Yeah, we surface something to the algorithm developer and we ask them to do something interesting with it. OK, so once we started working together, we could ask how interesting actually is this to like contemporary LM training. Probably go kind of fast here because it's like I think honestly everybody probably knows this in this room. In the vanilla version with this was literally just normal adaptive federated optimization. This is really not great. So here's where I think you start to see where differences maybe start to creep in between what's like the traditional federated perspective and something that's more data center focused. So if all you need to do is reduce, let's say, bandwidth requirements across your like multiple sites or whatever, there's no need for you to wait until n steps of training happen to do your synchronization, right? You can rather like iterate your way through the model, be doing something at every time step, and so you would like complete a full quasi-synchronization pass, even though nothing's ever truly synchronous, nothing's ever actually truly synchronized. because you are like walking the tree in this way. So by the time you get here, this guy has drifted a bunch. So this is something that starts to become more feasible in a data center setting because you don't have latency considerations about like, well, if this were all on phones, right, you would need to grab a new set and address them and like keep this thing going. You'd have a bunch of blocking in the middle. No, not going to work. But in data center setting, yeah, sure, no problem. And if you take this perspective, you actually notice that you can do something quite interesting, which is implement a completely non-blocking version of this algorithm. So you have synchronization points, but you have the entire step to do them by delaying when the fragment comms happen. So if you delay them till the next step, say you've sliced your model 100 ways, you're losing at most 1% of your compute for that step because you can just overwrite your synchronized thing into the appropriate slot. But as long as you can get that tiny little fragment 1/100th over in the entire step time, which is usually way like much less of a requirement for your bandwidth to do this training than normal data parallel, right? Because data parallel actually has to finish this reduction at this step time, which means that, right, you have this tiny little thing. Guess what? Whole step for a much smaller fragment of the model. Yeah, you can do this in a completely non-blocking way, fully pin your chips. But it doesn't really matter if you can do this in a non-blocking way if it's really not a good idea, if it's not going to work. But you know what? It does, perhaps surprisingly. And you can actually get much more decoupled than you would probably have imagined. You can nearly match data parallel training flop for flop. So that's token efficiency, data efficiency. I guess I kind of skipped that for this audience, but in data center training, since compute is so expensive, you need to really care about how data efficient your algorithm is. Compute is expensive and data is relatively limited these days. You have to very much care about how data efficient your algorithm is, which is quite different, I think, than much previous considerations in FL, at least the way that I used to do it. You really didn't care about that kind of data efficiency. In fact, you can, a lot of my work here started because I was asking the question, how data efficient actually is federated learning if you really tuned it really, really well? Turns out a lot more data efficient than I thought it was going to be. But yeah, you can really get effectively the exact performance of data parallel training with approximately 1% of the required bandwidth. And this has been replicated. So this is some startup made this plot. Yeah, okay, so here's an interesting thing. I guess I also bit my own slide here. If you want to scale distributed data parallel training, you can train the same quality model while cutting your bandwidth requirements by actually 2 orders of magnitude. I even undersold it, right? So, yes. All right, but do we really care? Do we really care about this? From the perspective of sustaining technology, there's this what's it called? Innovator's Dilemma, right? That's the book. It's like disruptive and sustaining technology. Disruptive is like you're going to make some new market and a bunch of new applications are going to come online. Sustaining is like you're going to keep doing what you already know how to do, but you're just going to do it better. So we're only going to focus on the sustaining angle. Whatever, I'm at a lab, so I have to focus on the sustaining angle. It's my job. From the sustaining angle, this kind of thing only really matters if it can scale. Okay, so how does it scale? We had a paper earlier this year which ran many experiments computing scaling values for this method, as well as a very well-tuned baseline called NanoDo. That was another group we work with reasonably closely. These results were shockingly quite good. I promise there was no cheating. I didn't lead this work, so you don't have to trust me. Somebody who's much more, rigorous than me led this work, which is nice. So I'll present a couple of findings that I think, for an FL audience are still quite interesting. The first one is that many replicas, we call it replicas even though they're no longer truly replicas because, right, you don't share your parameters anymore, but whatever, we just never come up with a better word than that. So many replicas scale better than few, and both scale better than data parallel training, right? So this is a line plotting relative evaluation loss. By the way, there's a bunch of other plotting methods that I can't show you. So like, yes, if you have problems with these, they're not ideal, but this is the right story. Trust me. This is all tuned over everything, batch size, learning rates, whatever, all your choices. These were single shot extrapolated. These are relatively low M values. Don't ask me if we can get M a lot higher. Hopefully you'll have that question answered in a couple months. So don't ask me yet, because I can't tell you yet. Both scale better than data parallel training. Horizontal scalability is good. There's this notion of critical batch size where if you linearly scale up your batch size and scale down your number of steps and appropriately tune everything at the appropriate sizes, you'll get perfect scaling with respect to the amount of compute you need until you hit a critical batch size, in which case you need, and you start getting worse scaling. So you can kind of speed yourself your training for free by increasing your batch size up to a point. That points to critical batch size. Yeah, that's kind of what you see plotted down here. Critical batch size is higher with these kind of local training methods. I think that's not actually shocking. And it increases with M, which I think is also not shocking. M, number of replicas again. Somewhat surprisingly, if you're training with a value that's larger than your critical batch size, you might already be in the regime where these kind of methods are actually just pure wins for you, right? Look at how bad this curve, this red curve is spiking up compared to these other ones. To me, I found that to be a very interesting observation, especially because most people don't really have the capacity to truly train at subcritical batch sizes, especially because it usually takes so long. The way the hardware works today, bigger batches make the hardware more efficient. So people tend to train at bigger batches than they probably should, because it's relative to something called MFU, which is model flops utilization, which is like how well are you utilizing the hardware underneath you. It's kind of better to take a training hit to get the speed up. Okay, so there's a very, very complicated story about batch size in contemporary training, but if you want to train at larger batches, which is very good for very many reasons, you actually probably should consider this kind of algorithmic approach. Finding 3, tuning is not too crazy. Of course, any more general method will outperform given enough tuning. So if you're going to do something new, you better check that you don't need to spend a ton of effort in eking out your gain. At least the major quote-unquote outer optimization values for what we do can be tuned at small scale and treated as constants, which is quite nice. Actually, both of the two values that we need to tune can be treated in this way. Okay, great. So there's some algorithm here. What's next? I actually think, I wrote this part of this talk for a very different audience, and I think it's worth highlighting here that all the stuff we just talked about is pure application, right? There's really not very, very little that's new in there. It's just a different way of measuring stuff that people already do that tells you it might become a lot more on the critical path for big training runs than it has been. Okay, again, this is only an example of the kind of yeah.
I think I'm confused about that plot. What was M again?
Which one? M is number of replicas, right? So it's number of clients in normal FL.
So then why is there a single data parallel baseline in that plot?
Because you can arbitrarily data parallel, right? It's the same computation. You're just changing how the computation works. It's mathematically the same. But when you change M, it's not mathematically the same anymore. Yeah. Yeah. So true data parallel, right, could be implemented
in a serial fashion, basically. It's a serial implementation of data parallel.
Yeah. The data parallel changing this value, what the analog of this value.
Does not. Okay.
Theoretically, it doesn't change what you're computing, right? If you have infinite precision arithmetic, it's the exact same thing.
Another thing, you're plotting this for fixed compute for all methods?
Yes, everything's fixed. Compute's always fixed. Yes, compute's always fixed. Yeah. Yeah, that's, I think, an interesting point, right? So when I say tokens are fixed, or we're looking at the number of tokens, Contemporary LLM training is usually done or studied in the quote unquote compute optimal setting. So it's like you do 20 tokens per parameter. So compute and number of essentially amount of data are always interchangeable when you do this kind of analysis. It's like people fix one value and it kind of determines both. The flops budget, like how do you split it between model and data? Yeah.
So I'm
Yeah.
still missing one thing. So when you change M,
Yeah.
you're saying the method changes. Maybe I didn't understand the method.
Yeah. Because you're doing this right? You're like, okay, let's imagine we're not doing this fragmentation stuff. You have when M is 2, right? You have one model here and model here, and you're evolving them for a while independently, and you're doing something to bring them together, right? And now you're synced. Then you come back, whoop, whoop, back here. But now when you have 8, you have to do this operation to all of them, right? So you have 8 independent copies that are all trained on a much smaller subset, right? So like you have a fixed amount of data, and the question is whether you give, let's say you have 8 examples and you want to either do 2M or 8M. This would be like I trained these on 4 examples and I didn't train these guys. Now I train this on 1 apiece, right? So it's like this thing doesn't commute. You can't just because you're doing this crazy nonlinear thing, taking a bunch of
It's partition of the same data set, right?
Yeah. Yeah. So it changes how you partition it, right? But the normal data parallel, because it's just derivative, everything's linear, you can just partition it, whatever, do your reduction, you're fine. Now you're integrating a curve here, so you can't it's all out the window. It's not, you're not doing the same thing when you do it with 2 or 8. Yeah.
I mean, do you have the ability to partition the data set however you like, or do you just assume this is a random partitioning of the data?
You can actually partition it however you want, but we've never studied it.
Do you
We've
have
always
any
done it
intuition
random.
on how we should be partitioning it, or you think random is fine?
There are people who are studying this exact question in reinforcement learning and post-training world, I want this guy to be good at math or whatever, and this guy to be good at, I don't know, I'm a mathematician, so what's more important than math? Right? This is algebra and this is analysis. How can you preserve them both? Yeah. People are starting to study that, but it's very understudied. No one really has studied designing this thing. Because we've mostly been thinking about pre-training, it's let's chuck all data considerations and do it all uniform and only focus on if I want to rearrange the computation in this more decoupled way, what are its empirical properties?
But we do know that at least in some simplified models, this second order similarity, I understand these are different assumptions, so on is exactly what makes these kinds of methods faster. And that would suggest that one should have as similar data as possible, which means some kind of random permutation would be best.
I buy
Random
this.
and partition.
I buy it. I generally speaking buy this. I think it's unclear when it comes to things. In the pre-training world, I for sure agree. That's why I've been why would we ever try to design this for pre-training? When it comes to things like post-training where your model's only moving a tiny little bit and maybe you actually want to separate and isolate effects a little bit more, I think I could imagine that my bias there could be wrong. Yeah. I'm not sure. I don't know. People are studying it. Will they succeed or will they fail? My guess is they won't succeed, but I've been wrong before and I could be wrong again. Yeah.
So another quick question.
Yeah.
Now I think I understand. The data parallel baseline is just a mini batch method. It's not the best data parallel method.
No, it's the best.
If that's the case, then if it has local computation as well, then changing M will change the algorithm.
Yeah. Well, wait.
But you said it can be implemented in a serial fashion.
Okay, what do I mean when I say data parallel? I mean this. I mean the following algorithm. You have some number of model replicas, and these literally have the same parameters. And now I get a different batch, like x1 and x2 over here, and each of these compute a different gradient. And now I average this gradient, G and G, and then I compute my next
So,
MN
so
prime.
It is a mini batch method. Okay. Yeah.
It's like this.
So it's a mini batch method. It's not doing sequential updates locally.
Yes, okay, yeah. Yeah, I mean, it's literally computing a derivative and applying the derivative, right? You know, like, just a way of computing a derivative and applying a derivative. A single derivative to a single global model.
I think the issue is we just came from a tutorial where we saw many data parallel but not mini batch methods. So I was thinking of.
Okay, well, yeah, I mean, arguably these are all, it's just a name, right?
It was there too. It's just-
No, but we saw other methods also. But here it's just mini batch in the baseline.
No. But
Here it's just mini batch.
I'm just using data parallel as a name for an implementation, yes.
Actually, now that we're slowing down, like, so the diloco method, which I'm not sure I totally followed what you're doing to aggregate. So you're evolving, let's say you've got 8 models, you're
Yeah.
evolving them separately for some amount of time.
Yeah, more or
On
less.
on disjoint data sets,
Yeah,
right?
Yeah.
And then you're doing some kind of aggregation. Is
Yeah.
that what? Can you say a little? Are you just averaging model parameters or like?
it's like a normalized version of this. So it's like separately average the magnitude and the direction, basically. So it's like not that far from averaging, except, right, averaging in high dimensions means you're like making something smaller. So like, don't do that. You know, don't do that version. I usually kind of skip that because I'm like, I think, we haven't done a ton of research in the merging, just like picked one that works and explored it. Yeah. Anything else?
So again, the averages. What you're doing is you're looking at the differences between the original model and the new model that you got at from each of the 8 copies. That gives you sort of a bunch of different directions and magnitudes.
Yeah.
And you're going to separately average directions and magnitudes. Is that what you said?
Yes, and then you're going to get a single global thing, and you're going to treat this as a pseudo gradient, and you're going to feed it into an outer optimizer. I don't like that terminology, meaning like a mathematician, right? So gradient means a derivative in my mind. When you average a bunch of things that are a bunch of integrals, it's not a derivative anymore, but we call it pseudo gradient. The only thing that's happening in the outer optimizer here, all the additivity, so all the preconditioning and everything is all in the inners. The only thing that's happening in the outer optimizer here is a Nestor momentum, and that's it. Yeah. So by the way, the semi-equals 1 you see is way under this red curve. So you can implement like outer optimization with Nestor momentum with no distribution, right? You just take a bunch of steps, compute a difference, feed that into like into a momentum-y thing. So you have now an estimate, like you have effectively a trailing average of where did my model want to go after n steps. That's what this really, really low m=1 value is here. There's some other people from optimization world, a bunch of people from Meta that are studying that with no distribution at all. Because it's really good, surprisingly. Especially surprising because it's just purely linear post-processing of everything. So like honestly, it's a little weird that it works. If you take the classical perspective, it's strange that it works. You shouldn't expect it to work, probably.
Sorry, question. So and then for evaluation, you evaluate across the M models and you report the average?
So actually, this evaluates the resulting synchronized model. So this you don't evaluate an ensemble here or anything. You evaluate the resulting synchronized one. I guess I threw my other plot away. Yeah, and it's even weirder in the fragmented case because, we grab a slice of each model and synchronize it each step. So that results in this outer model that has never had gradient steps taken on it. It's just the result of the fragment of the synchronization that happened in every step, and that's when we evaluate. So those being good is honestly bizarre, but they are good. Okay, do I have many more slides here? Probably not. Let's see. Okay, yeah. We show that this systems feature, the stuff we just talked about, you can leverage it at a minimum for systems reasons, but also I think it's worth noting that There's room to leverage this feature and improve on core optimization algorithms we all know and love in the contemporary setting, like data parallel training, which is like, sure, do real replication of your model parameters. Yeah, that's the end. All right, all questions are welcome. Yeah. So.
Do you have intuition on why you chose to separately aggregate the direction and magnitude as opposed to locality?
It's really just it's just to preserve the norm in my mind, because yeah, like whatever. Here you go. Basis vectors, right? Now you average these things. This is 1, 0, or is it 0, 1? 0, 1, right?
So I can just say something to the people who are in my tutorial. So I mentioned this Nastya algorithm that actually explains this. This is one of those extrapolation methods. It's very clear there why this must be the case. The reason is because the pseudo gradient actually has good direction, but it has bad scaling. The scaling is not correct. So when you aggregate the pseudo gradients, you have to normalize if you want to do it properly. And then you have to find the right scaling factor, which is the extrapolation thing, which is what the auto-optimize does. And it is a very good explanation of why. Imagine that locally you do many LGD steps, but with tiny step size.
Right.
If you do one pass over the data, you basically get the true gradient direction, but completely wrong scaling.
Yeah.
So you have to scale it normalize, and then you have to rescale at the circle.
So it's kind of like Emmett's paper, for instance, right? Like the outer step size has to accommodate
Yeah,
for
that's
the...
exactly what this FedEx P and FedEx and Nastya, those papers that I recommended you for reading to explain.
Which I mean, correct me if I'm wrong, but I would imagine it's basically this, right? It's like you average these things. This guy's gonna be too small. In high dimensions, it's off by root n. This is a root 2 hiding in here, right?
So
L2 norm.
I see.
Yeah.
So could you get the same effect by using local STD with inner outer step sizes, but tuning both of them? Because here you are sharding the data ID.
I don't know if it could be done transparently. Like the question is about whether it's all linear, right? Like, you mean, can you retune the outer step size and like refix this? Maybe you could do it in a per parameter way, but per layer way, right? Because number of dimensions in your layer is going to like actually affect what this kind of effect is for you. If you have a 2-dimensional layer, it's going to be root 2. If you have a 9-dimensional layer, it's going to be root n you need. So, like just to correct for this effect. If there's more, then you have to do more too.
Yeah, it's actually exactly my question. So when you do averaging, is it do you flatten all the vectors, like all the parameters on one vector, and
No.
average them you do it per layer, right?
Yeah.
Do you have different learning rates for different layers?
Nope. Yeah. So yeah, I mean, you could imagine a lot of stuff in designing outer things. I think we honestly don't know why that m equals 1 works so well. I think that's an open question.
And equals 1, what do you mean?
So you do this pseudo gradient thing with a momentum on the long term differences, right? But you do no distribution at all.
N is your capital N, number of
Yeah.
replicas?
Yep.
Replicas?
Yes.
So if you do this with one replica,
Yeah. Works very well. And where?
but this is the same thing as
Here. It's data parallel with like a long range momentum augmented in it. It's a really weird algorithm. Honestly, bizarre. Maybe we can do picture. It's like you take.
Momentum, but every once in a while, instead of doing like it at every step. So it's a. But if you had more clients, then the outer step size would be.
Like you take a bunch of steps, right? You treat this. There's no replication. There's only one model now, right? There's no distribution at all. You take a bunch of steps. You treat this as a pseudo gradient. This thing goes in. You accumulate this into a momentum buffer. You come back here. So your momentum buffer is now whatever, some other vector that's been influenced by this, but it's not exactly this. It's like similar but not the same. You come back here and you take the step in the direction of your momentum buffer's vector. Very strange, very weird. Yeah.
Quick question, and this is weird, yeah, I agree.
Yes.
The m equals to 1 case, you are tuning the step size separately for each experiment still.
Yeah, everything here is fully tuned over everything. This
It's
one is
not,
fully tuned over.
It's not just a scaling issue that this frequent momentum somehow helps.
Exactly, right, yeah, yeah. Everything here is fully tuned over everything. That's why I made a point to be like, there's no cheating here. It's like, everything here is crazy tuned with tons of compute over everything.
What's precisely the inner and outer optimizer? Is inner optimizer just SGD?
Oh, it's Atom W, I think, right? Because like we need, yeah, this is LLM training, so it's like we really need that preconditioning.
And outer one is what?
Has to do with Nestor momentum. Nestor momentum is usually better than Polyak, but it's all in its Optax implementation. So the only difference between those two is it's the relative weighting between the new gradient and the momentum buffer. Yeah, the momentum buffer is actually the same. It's just the relative weighting of the new gradient and the momentum buffer in the update. Yeah.
What about Atom as an outer optimizer?
So yeah, we haven't never had a
I think
ton
you
of
mentioned it doesn't work, but
yeah, we've never had a ton of success in stacking those two, or in stacking adaptivity inner and outer. I do think that makes sense because, like, if you view, that's one reason I don't like the term pseudogradient, because it's like, it's a really different thing, right? Over whatever, 30 steps or something, this is a completely different thing than a gradient now. Especially because if your inner preconditioning is working, you know, if you take the like Newton style view of preconditioning, which is like this, your optimization value is all long and narrow and messed up, and you're just flattening it out, right? You shouldn't need to flatten it out twice. And then there's a bunch of other problems with Atom, in my opinion. Like, you know, I think I did this analysis a while ago, so I'm going to try to pull it off the back of my brain, which is that it looks too much like sine SGD in this world. And these, you're probably leveraging exactly like, exactly magnitudes, not sines, when you do this like long range thing. So yeah, we've never successfully stacked adaptive inner and outer, but you can put the adaptivity in either. I just think adaptive inners probably makes more sense for like LLM setting, because yeah, those gradients are totally messed up. you need to precondition them.
Quick high-level question.
Oh,
So
you're
okay,
over. You're too far away from everybody else. I can't see.
So I'm thinking of DLOCO as an instantiation of adaptive federated optimization, where you have Atom W running locally.
Yeah.
The outer optimizer is Nestor. Okay, so
Yeah.
this is one instantiation of this that seems to be particularly effective
Yeah.
for looking at LLM training in this data center environment.
Yep.
Where do you go from here? Like, is this are we done now? Is this the most efficient method? Or like, where do you think the biggest bottlenecks are? If you were to try to improve the method further or try some other variant, like what would be the most promising thing to look at there? This is
Yeah.
purely speculative. I'm just curious about, you know.
That's a good question. I think I'll have to think about like what I can say.
Okay.
One thing is, you know, we studied its scaling reasonably well in this paper. Like, I think we studied scaling well enough to motivate further study of its scaling. That's, but I don't think we closed the book on its scaling, in this paper at least. Will the book be closed on its scaling in the future? Possibly, but that's not like, I guess that's not an answer to your question. That's not an algorithm, right? That's like that's not an algorithmic change. It's like it's a bit more like a de-risking-y kind of thing. I think from the algorithmic perspective, actually, it's this fact that m equals 1 is really good that is like freaks me out the most. Of all the stuff that we've talked about here, that really doesn't sit well with me. I really don't like I mean, this is standard, right? There's no distribution here. This is like I'm just talking about a single model and I'm computing gradients, I'm taking steps. And now like I'm doing something different every 30 steps or something, and that's actually working for me on these really well-tuned baselines. Like, that seems honestly bizarre. If any of you all know Aaron DeFazio, he just put out a paper on something called GPA. So, and we never publicize this name, but we call this SLA for like super look ahead, because it's a lot like look ahead, but you just put necessary momentum on here. I think that was only internal. He just published a paper on GPA, which is, it's like inspired by the fact that this looks really good, but is really weird. I think, I would say like, thinking about the statistical, okay, two things then. Thinking about the statistical fact of like, this is some other piece of information than like a pseudo-gradient is. It seems like we can leverage it for something, but why? And like, what is this piece of information? Should we understand it as like a James Stein estimator style thing? Should we understand it as like, I'm squeezing more information out of my noisy batches by accumulating them at some other time scale? Should I understand it as like a fundamentally dynamic thing? I have a collaborator who proposed to me that it's like this, that it's like if I'm in a sharp eigenmode and I'm damped, so I'm taking a step here, I'm taking a step here. When I do this outer thing, I don't see this, and it looks like I'm in a narrow eigenmode, like I'm going right down here. So like maybe I can accelerate it more like that. Is that the right explanation? I don't know. So okay, that's one. And what was the other? It was something about distribution. Maybe I'll have to get back to you on that, because I probably have forgotten it. But this is one, and the other I'll probably answer later. Yeah, okay.
So
Audrey
this
is next.
M equals to one thing.
Yeah.
It's bizarre, but is
Yeah.
it any more bizarre than the fact that frequent learning rate decay works when you're training image models? That's a fact.
Frequent learning. Oh, you mean the like seesaw thing, like this?
Either
Learning
that
rate?
or even like monotonically decreasing over time is usually better than either constant or just keeping to decrease. I mean, these are all bizarre things that happen. I'm saying even in a serial setting, it's not
Things are weird.
unheard of, right?
It's true. Yeah. Yeah, I mean, I do think like it's generally underappreciated that like it's not even really obvious. Let's say you're doing SU with momentum. What even is your learning rate? Like, which one is your learning rate? Is it the multiplier you apply to your recent gradients? Is it the multiplier you apply to all gradients in the long term? Or is it the like multiplier on your basically L2 norms of everything? Because these all give you different values. It's not that thing. Like even the answer, what is the question, what is learning rate in normal training is not obvious how to answer it. So like there's a lot of bizarre stuff. I agree. I don't know that I can comment on which is more bizarre than which. It's all bizarre, I think. Andrea had a question.
Yeah, I'm trying to understand. So, you train until convergence in each of these models?
No.
You gave them the same amount of compute
Yep.
with unlimited bandwidth in a way? Or
Wait. What? I missed that
No,
last
I'm
one.
thinking it's sort of like passing data around is not a concern, really?
Is not what?
It's not a concern. It's not something you're quantifying
Yes. So like,
freely?
actually the number of bits communicated is strictly decreasing. Well, these are the same, then it's strictly decreasing this way, but it's not quantified here.
Okay.
Yeah. Because essentially it's really coming from like, let's say I have a bunch of data centers that are all, I got one in the Sahara and one in the Mojave or something, and I can't lay a fiber between them. So I need a low bandwidth connection. I'll probably use something like this. If I got 8 of them, different places, and I don't have a fiber connection between them, I'll probably use something like this, right? Like, it's like that. So it's not, there's no like, we don't do a smooth quantification of the comms. We rather like view each one as a separate algorithm, basically. It has its own whatever application. Yeah. I think there was one over here somewhere.
Yeah, maybe last question,
Okay.
just to
Yeah.
make sure you don't go too late.
You actually kind of answered the
Oh.
question with your previous answer.
Okay.
Like, I was just wondering, like, you spent a lot of time on this slide. I couldn't tell if there was like a case where increasing the number of replicas would be useful, and you kind of indicated.
Yeah,
that it is.
that's why.
Yeah.
Yeah.
You know,
That's why, is that, yeah, bits communicated go strictly down as you go along these guys, this way. Okay?
All right, let's thank Keith again.
Yeah, yeah.